All right, so here we go with part 2 of section 2.4. We're going to take the idea of one-sided limits and keep talking about it. We're going to use that idea of one-sided limits to discuss continuity on a closed interval. That is, to find out where a function is continuous and how it could be continuous on a closed interval. Okay? So here I have a graph of a function that is continuous on a closed interval. You'll notice it has solid dots on both endpoints. And our definition of continuity says it has no holes, no breaks, no jumps, no gaps. But our definition said, number one, that to be continuous, f of c must be defined. 2, that the limit of f of x as x approaches c must exist. And then number 3 was that the limit of f of x as x approaches c must equal f of c. Those were our 3 requirements for a function to be continuous. Well, number 2 and number 3 here made endpoints impossible to talk about in terms of continuity, because for a limit to exist, you would have to be able to approach the endpoint not just from one side, but from both sides. And since this piece out here didn't exist, we couldn't talk about continuity over there. Same thing with this other endpoint over here at B. You could approach from the left, but since you couldn't come in from the right, we couldn't talk about continuity over there. So we couldn't, wait, that should be a sad face. We couldn't talk about continuity on a closed interval because those endpoints, we couldn't take limits at them. So what we're going to do is we're going to extend the definition of continuity to say, hey, if you happen to have a closed interval and the proper one-sided limits work, that is, the right-hand limit at the left edge and the left-hand limit at the right edge work, then we'll say that that function is continuous on that closed interval. So going back over here, with our new definition, we don't care about this side, and now we can say, yay, because it comes in from the right, okay. And we don't care about the right side, so we can say, yay, because it comes in from the left. And since those one-sided limits at those endpoints work, that is, the one-sided limit is equal to the functional value at those endpoints, we can say that this function is continuous on a closed interval. Right? So one-sided limits allow us to take that continuity idea and make it a little bit stronger, take it to those one-sided limits. All right, so now we're going to get to the properties of continuity. What you might have noticed so far is when we talked about continuity of functions, we kept ourselves limited to simple functions that we knew what the graph looked like, so we could easily take a picture to make a sketch of it and talk about continuity. So we kept things to like 1 over x or sine x or relatively straightforward functions. These properties of continuity are going to allow us to extend simple functions and make them into complicated functions. And so it starts out by saying some ifs. B is going to be a real number. F and G are continuous functions. Then the following are continuous. B times F. So if you take a continuous function and multiply it by a number, it's continuous. The sum and difference. Continuous plus continuous is continuous, and continuous minus continuous is continuous. The product, continuous times continuous, is continuous, and the quotient, continuous divided by continuous, is continuous with the one exception that we can't divide by 0. And what these properties do is they allow us to extend even further and say all of these things are continuous on their entire domains. So all of the functions you've been working with throughout your entire mathematical career, the polynomials, the rationals, the radicals, the basic trig, exponentials and logarithms, these are all continuous functions on their domains. Okay? Now that little piece there on the end is why you spent so much time in your college algebra class discussing What is the domain of this function? What is the domain of this function? What is the domain of this function? Because we need those domains. We need to know those domains so we can figure out where things are continuous, where they're discontinuous, so where can we do calculus on them. Okay? So, let's go further. Discuss the continuity of the following functions. All right. Where is the natural log of 3x continuous? Well, logarithmic functions are continuous on their entire domains. So what is the domain of the natural logarithm function? Well, the domain is 0 to infinity. So where is it continuous? It's continuous from 0 to infinity. All right. Where is the function g of x equal to the square root of x plus 1 continuous? Well, it's a radical function, so it's continuous on its domain. So it is continuous whenever x squared plus 1 is greater than or equal to 0. Well, x squared plus 1 is greater than or equal to 0 for all x's. So its domain is from negative infinity to infinity. So it's going to be continuous from negative infinity to infinity. How about k of x equals sine of 1 over x? Where is it continuous? Well, sine is continuous everywhere. So as long as 1 over x is defined, it's continuous. But 1 over x has issues. 1 over x has an issue if x is equal to 0. So the domain of this function is going to be all reals except for 0. So negative infinity to 0, union with 0 to infinity. And that means that it is going to be continuous on its domain. That is negative infinity to 0, union with 0 to infinity. Now what you might have noticed is that all three of these functions, while they are a logarithm, a root, and a trigonometric function, they are also all composite functions. And the theory, or the theorem about composite functions says that if g is continuous at c, and f is continuous at g of c, then the composite function f of g is going to be continuous at c. How does that work again? If g is continuous at c, and f is continuous at g of c, then the composite function given by f of g is continuous at c. All right. So do you remember how composite functions work? We start here, go to here, and then go to here. So we're starting here at c. We're going over here to g of c, and then we're going over here to f of g of c. And so for continuity to exist, this must be continuous, and this must be continuous. So g has to be continuous at c, and f has to be continuous at g of c. So if we're looking for discontinuities, we're looking for any value here that would break this one, or we're looking for any value here that would break this one. So when I was working up here, I said the root has to be greater than or equal to 0. The radicand can't be negative. So I said, when is the g function, that's this guy, right? That first step, greater than or equal to 0. When I looked at trig, I said sine works everywhere, so this piece works for all reals. So when is this bad? Continuous functions, composition, look at both pieces, look at both steps of the function. If there are breaks in either of them, it's bad. Okay? The uses of continuity, well, we can use continuity to extend the ideas of limits out. Right? Remember when we were doing direct substitution and we said when you get a limit, just put it in and see what happens? Continuity is the property, and it gives us the theorem that says that we can actually do that. We were doing it without having the theorem. Now we have the theorem that says you can do what we were doing. Right? We can extend that out to also work for transcendental functions, radical functions, and composite functions. So anytime we see any of these types of functions, polynomials, rationals, trig of any kind, exponentials, logarithmics, roots for which they're defined, and composite functions that work for continuity, we can take limits by just simply doing direct substitution. So even though we're talking about continuity, our focus is still on limits. Everything is always about limits. Okay. So what do they tell us? If you know it's continuous, evaluate the function by direct substitution, you're done. The last thing that they toss at the end of the section is something called the intermediate value theorem. It's in this section because the definition requires that we understand continuity. And so let's take a look at the intermediate value theorem. The intermediate value theorem says that if f is continuous on the closed interval a, b, and f of a is not equal to f of b, and k is any number between f of a and f of b, then there is at least one number c in the closed interval a to b such that f of c is equal to k. Now, I love definitions like this, but let's see what it really means. All right, so I'm going to break it down piece by piece. First thing is we have a continuous function, and it's continuous on an interval a to b. So I'm going to come down here on my graph, and I'm going to draw an a to b interval. And f of a cannot equal f of b, meaning the starting y value is different from the ending y value. So what I'm going to do is I'm going to say, okay, here's f of a, here's f of b. And I have to draw a continuous function from this dot to this dot. Now, pick a k, pick a value k that is any number between f of a and f of b. So pick any k on that y-axis, so k. The intermediate value theorem says there is at least one number c in f of b such that f of c is equal to k. No matter what k I picked, if I had picked a k further up, then c would just be further over. If I had picked a k further down, then c would be closer. If I had picked a negative k, it'd be over there. So basically what we're saying is, if you're here now and you're there later, you have to go through every value to get from here to there. Okay. Now, almost always when you look this theorem up in a book, it is going to be drawn something like this, where it starts low and goes high. There is nothing about the definition that requires that you start low and go high. I could erase this entire graph and redraw it and say that A is here, B is here, f of a is here, and f of b is here. Right? And I don't have to, if I want, I could wiggle a whole bunch as long as I draw a function. And now if I pick a k, like say this one right here, now there's 1, 2, 3 values, a C1, a C2, and a C3, where all of those would give me the same k value. Now, one of the earliest uses of this intermediate value theorem was finding these important points right here, here, and here, finding zeros. And the way that they usually did it was, is they would find an interval where the function was above the x-axis at one endpoint, below the x-axis at another endpoint, and slowly reduce the size of that interval until they could walk in or capture the zero that they were looking for. Usually what they would do is they would take the distance between the a and b and divide it by 2. So they would chop this distance right here in half, and then look to see if we're still above and below. Chop it in half again, look to see if we're above and below. Chop it in half again, look to see if we're above and below. Usually picking one of the endpoints and moving it. Right? So they would slowly move A in until A went negative, then they'd move A back, and then they'd move B in until B went positive, and then they'd move back and forth, walking in on these zeros. It was an early approximation technique. It'd be a really easy technique to write an algorithm for, to write a loop for, to code it. And so that's why it was used. We don't use it as much anymore. There are always theoretical applications for it, but its application has lessened in favor of other techniques for finding zeros. Okay? But this brings us to the end of the section 2.4. Okay? Just really quickly, some notation. This theorem is called an existence theorem because it tells us that that value c exists, but it doesn't tell us how to find it. Okay? It just says it's out there. And again, remember, it only works for continuous functions f. All right, this is the end of section 2.4. The next video will be section 2.5.